And I'm already like 18 minutes late to fluid mechanics. This is an awesome sunset though.
At a different rate, which is what? Yeah, it's the difference of these two, right? V1 minus the control volume velocity. So this is, I think most books tend to use W as the relative velocity. So it turns out what's important in that case, and again, this is for a control volume moving at a constant velocity, not accelerating. So it turns out that if we went back and did this whole derivation again, we would come out with the exact same thing for a constant velocity control volume, except okay. And there's a it couldn't be more simple. There's a simple proof basically that you know, if we take what used to be the absolute velocity, so let's define V as the absolute velocity. Let's define V sub control volume as the control volume velocity, and let's define W as the relative velocity, absolute velocity, and some control volume velocity, that this has to be the relative velocity. So in other words, the relative velocity is just the absolute velocity minus the control volume velocity. I mean, here we found that in scalar form, but that's true in vector form as well. So doing problems where there's a constant velocity control volume is nothing more than doing what we did before, except first figuring out what the relevant relative velocities are. It's not that we couldn't get these on our own, but they're very much easier with this tool. So, for example, conservation of mass. Like we said before, B is the extensive property. So if we're talking about mass, B itself is the mass. And the intensive representation of mass is what? Whatever the extensive is per unit mass. So in terms of the intensive property of mass, it's just unity. And over here on the system side, if we remember what we said about the way a system is defined, in the Lagrangian sense, a system is a fixed collection of particles. And this stuff moves along, and we can imagine sort of change of mass with is that dm dt for the system is 0. So that is our conservation law for the Lagrangian representation. But again, not very useful for solving problems. However, this law, this 0, is equal to what's on the right-hand side, which is useful for problem solving. So if we simply plug in this little b is equal to 1 on the right-hand side, we instantly write down what becomes our integral of rho times 1 dv, so we'll just write rho dv, plus the surface integral of rho times 1 times v dot nda, or we'll just write rho times v dot nda. Okay, so that's conservation of mass in integral form. Completely general, no assumptions about incompressible flow or anything like that. And what it says simply is, again, if we look at what the physical meaning of these terms is very carefully, it says that if we take the sum of this term, which represents what? It represents the density times a differential element. So mass per unit volume times a differential volume, so the mass of a differential element, and integrate that differential element over the entire control volume. So what's in the triple integral here is the mass within the control volume at an instant of time. And so if we take the derivative of that, so d by dt of the total mass of the control volume at that instant of time, and so if we take the sum of that plus, what is this? So remember v dot nda, that is our that is our net volumetric flux through a surface, right? In fact, it accounts for the fact that the vector and the surface by the unit normal may not be oriented. In fact, they may be opposite. This takes care of its own sign, whether stuff is crossing this way or stuff is crossing the opposite way. So this right here represents, for a differential element of the surface, the volumetric flow rate. And if we multiply by the density, we get mass per unit volume times volume per unit time. So this is the mass per unit time in that differential element. And then we integrate that over the entire surface of the control volume. So this thing in words says that the sum of the instantaneous rate of change of mass within the control volume plus the net rate of mass flux over the boundaries of the control volume is equal to 0. The sum of those two things is equal to 0. Okay? And like I said, we haven't assumed any sort of incompressibility condition here. This accounts for the fact that we may be compressing the mass inside the control volume. This accounts for the fact that the control volume itself may be changing size and so forth, or the amount in the control volume may be changing. For example, we'll do kind of a fun problem I call the bathtub problem, because basically it's a bathtub where you take the control volume as a whole of the bathtub, but only part of the tub is full and it's filling up. So the mass within the control volume is changing, even though the liquid in there isn't really being compressed. But if you look at it as a whole, there's more mass for a fixed amount of volume, and so it sort of gives the appearance at the integral level that the density is changing in the tub. Okay, so all of those things are rolled into here. And again, you can probably agree with me here that if we step back and we look at that, we would have been hard-pressed to derive that from scratch, right? But here, we did our simple little thing, plugged it in, and got this useful equation. Okay, so that guy is actually useful for problem solving. Version that does not depend on density. So, and let's assume we do that. So if we factor out density, if it's a constant, we can divide through by density. So for that case, we can just erase that totally, because on the right-hand side, we divide through by a constant, this side stays 0. And if, as well, if the control volume is fixed, so in other words, what's left here, if we do that, the integral of the volume element, so this is the control volume itself, if that is not changing with time, so in other words, for a fixed control volume, we get a very common form for incompressible flow, which is simply that V dot N dA is equal to 0 for incompressible flow and a fixed control volume that is all the way filled up, like we said. Okay. Now, what's interesting about that is we got that, and we did not assume for incompressible flow that this flow is steady state. So this applies for steady state flow and unsteady flow. The flow is incompressible. And if we look even more closely at the mathematics here, we find that this is simply the general form that we have been using a very special case of when we drew pictures like this. When we had this pipe and we said, let's have a control volume here, and the volumetric rate of inflow equals the volumetric rate of outflow. That's exactly what this says, right? Because if we extract this out, so let's extract out this control volume, and let's write down our unit normals, always outward facing. So on this side, this unit normal faces this way. On this side, it faces this way, because they always point outward. The top is fixed here. And the bottom, well, it'd be, the circular segment. So assuming the pipe doesn't have any holes in it, there's no mass that crosses this boundary. Mass only crosses this boundary, and mass crosses this boundary. So over here, our velocity is coming in this way. Over here, it's going out this way. So if we basically evaluate what this thing says for our simple case here, if we can assume that this is a uniform velocity. Remember, this thing doesn't even assume that the velocity is uniform. This is completely general. For arbitrary orientation of the surface, arbitrary velocity, and so forth. And so if we evaluate this thing, what this says is, let's call this left boundary, boundary 1, and this right boundary, boundary 2. And so if we write down this thing boils down to v dot nda integrated over boundary 1 plus v dot nda integrated over boundary 2, plus we would say integrated over the third boundary, the cylindrical part, except we know that there's no velocity going through there, so we can just drop that. And that's all equal to 0. Okay? So on the left, since the velocity points in the plus x direction and the unit normal points in the minus x direction, their dot product is simply v dot n in that case is what? No? Negative v, yeah. So remember we've got, so when we have the dot product, we have this trigonometric entity. So this is plus 1, 0, and then if we flip it all the way over, minus 1. So in this case, this guy is just minus v. And we'll do a straight multiply since this is a uniform flow. We don't have to integrate here. And dA then would just become the area. So this is minus v on the left times area on the left. On the right-hand side, we have v and n in the same direction. The dot product is plus 1. So we get plus v, I don't know, let's call that v1, a1, let's call that v2, and then times a2. And so that's nothing but v1, a1 equals v2, a2.